So I'll be talking about mathematical problems in quantum information theory and quantum computing. And I think the first thing to do is, first thing I want to say is that these are both, well, these fields both started reasonably long time ago, but there's been, most of the work that's been done in these fields has been done in the last 5 or 6 years, and this really isn't enough time to figure out whether an open problem is going to be easy or hard. So some of the problems I'm giving in this lecture may be quite easy, and some of them may be, very difficult. And in fact, I expect some of the problems in quantum computing are going to be very difficult because they're related to very difficult problems in classical computer science. And I'll concentrate mostly on quantum information theory. So one of the fundamental principles of quantum mechanics is the superposition principle, which says if you have two distinguished states of a quantum system, then alpha A plus beta B is another possible state of the quantum system. So let's see. Here we go. So if you have A and B, which are distinguishable through some kind of experiment, you can make the state, or consider the state alpha A plus beta B, where absolute value of alpha squared plus beta squared equals 1. And then if you're in this state, and you try to distinguish between A and B, you'll see A with probability absolute value of alpha squared. And when this,
you assume that A and B are orthogonal.
Yeah, I assume A and B are orthogonal here. And what this says is essentially that quantum states lie in a vector space.
They're observing, but why don't observe combination? They kind of.
Oh yeah, you could also observe, you can also test for alpha A plus beta B. And then you would test, so you can observe, if you have two orthogonal vectors, then you can distinguish between them. Now, if you have non-orthogonal vectors, you cannot completely distinguish between them, and we'll get to this point later in the talk. But another thing about principle of quantum mechanics is that evolution of an isolated system is linear, which just means you have a linear map on a vector space. So if you're considering finite dimensional vector spaces, you just have matrices. And in this talk, I'm just going to concentrate on finite dimensional vector spaces. There are lots of things get more complicated when you extend to infinite dimensional quantum mechanical systems, but there's enough open problems in finite dimensional ones that don't have to look any farther. And, well, an easy example now. If you have a photon and you look at the polarization of a photon, well, there's two-dimensional quantum systems, so you can have basis vectors, vertical and horizontal polarization. And other possible states, polarizations, are all linear combinations of these. So, for example, this is 1 over root 2 vertical plus horizontal, and this is 1 over root 2 vertical minus horizontal. And if you send this through this state through birefringent crystal, which separates out these two polarizations, half the time this will appear to be this polarization, so half the time the photon will go up, and the other half of the time it will just, say, go down. So if you have a joint state space of two systems, what happens is that the state space becomes a tensor product of the state spaces of these two systems. So, for example, in this if you have two polarized photons, you get a 2 times 2 dimensional space, and this contains states in which neither photon can be said to have a definite polarization by itself. So you get states 1 over 2 up, down, minus, or up, vertical, horizontal, minus, horizontal, vertical. And this is an EPR pair. These two photons are said to be entangled which means there's some funny, non-local quantum correlation between them. And we're going to be using entangled states exactly like this later in the talk, so don't forget about them. Okay. So first, I'm going to say a few things about quantum computers, and then I'll switch back to quantum information theory. So quantum computers are, okay, if you just have a two-dimensional Hilbert space and you're talking about quantum computing, we call it a qubit. And quantum computers work in the complex vector space 2 to the n, where n is the number of qubits in the computer. So here are all the basis vectors of this, or one set of orthogonal basis vectors of this space. And there are 2 to the n of them, and they're just tensor products of v0 or v1, where these are just a basis for each of these vector spaces. So right now what I want to do is define a mathematical model for quantum computers, which is equivalent to, so this is a very nice mathematical model, and it's also equivalent to nearly all the mathematical models of quantum computation that people have presented. And so for computation, you really need to input things into the computer, you need to take things out of the computer, and you need to change the state of the computer. So how do you do these things? Well, in this model, input is very easy. If you want to input an n-bit binary string, you just start the computer in the state, 001010, which means you start the first qubit in state v0, second in state 0, third in state 1. So this is just one vector in this large Hilbert space. Now the output, after we've done things to this vector, we're going to end in a state which is a general state in this space, which is just a linear combination of the v sub i's, where I goes from 0 to 2 to the n minus 1. And, well, you can't get this state from from the quantum computer because you can't observe the complete state of this quantum system. And in fact, it's sufficient just to observe it in this basis. So if you have this state, you'll see I with probability absolute value of alpha I squared. So this is a probabilistic step but quantum mechanics is probabilistic by nature. And in order to say we've completed it, we have a program that does this computation, we'll just require that we get the correct answer with high probability. And high can be 2/3 if you want, because if you can get it with 2/3 probability, you can just repeat the computation, and then you'll amplify the probability to anything reasonable. So thinking about quantum computers, it's nice to think about classical circuits for computation. And it turns out you can make well-known theorem, you can make any classical computation into a circuit, and you only need and, or, and not gates. And you stick 2 wires in the gate. They have values 0 and 1, and you get values on the wires coming out. And notice one of the things we don't allow is we don't allow gates that take n inputs and give n outputs. And there are 2 good reasons for this. 1, they're very hard to build. And 2, if we allow general gates like that, you could compute anything in 1 step, which wouldn't be much good for a theory of computation. So for a quantum circuit, we start with values on the quantum bits. So this is 0, 1, 0, 0, but these live in a 16-dimensional complex vector space, the tensor product of these things. And then what we do is we have either gates that link 2 of these wires or 1 of these qubits, and a transformation on these gates Well, we said quantum mechanical transformations were just matrices. So a transformation is just going to be a 4x4 vector for a 2-spin gate, or 2x2 for a 1-spin gate. And as soon as we apply something across a 2-spin gate, these two qubits become entangled and they no longer have a definite value. So after doing, so a program is just a set of gates, a list of gates. And then at the end of this, we measure what's on the gate, or when we measure a value of these wires and get a probabilistic output, and that's the output of our quantum circuit. And what it turns out...
So they must be huge, yeah? We have 2 to the n thing, yes? We have 2 to the n lines.
No, you have 2 to the n, no, you have...
Number of lines to the n.
No, the number of lines is n. The size of the of this complex space is 2 to the n, because it's the tensor product of n of these things. But each of these lines, you only have n lines, and if you want polynomial length computations, which, is, then you just have n to some power gates. And something that can be solved in quantum polynomial time. There's a circuit for, for each length of the input, there's a circuit with n wires and n cubed gates. And you also require that there's some way of constructing the circuit efficiently with a classical computer. Okay, what it turns out is that the problems solvable quickly on a quantum computer are qualitatively different from those solvable quickly on a classical computer. So there are some problems for which quantum computers speed up things exponentially, and there are some problems which it doesn't seem any easier to do on a quantum computer than on the classical computer. So it's a different model of computation, and well, here are some examples of problems solvable quickly on quantum computers. Well, the one that, around 5 years ago, I showed that prime factorization was solvable quickly. So the best way we know of factoring large numbers into primes on a classical computer requires roughly e to the cube root of L steps, where L is the length of the number. If you had a quantum computer, and nobody's built any of them yet, although they've constructed itsy-bitsy prototypes, you could do it in L cubed steps and smaller if you want to do a little bit more sophisticated. And you can also speed up, the same speed up for discrete logarithms. And it doesn't really matter if it can be discrete logarithms over elliptic curves or any abelian group. And also, it appears that certain quantum mechanical computations can be sped up considerably with quantum computers. For example, quantum computers are very good at simulating quantum mechanics, which shouldn't be very surprising. In fact, that's what Feynman originally proposed them for. And Love-Grover has also showed that you can get a modest speed up for exhaustive search from, if you want to search, a space of n things, it's, takes n steps on a regular computer, and you can do it in order of square root of n steps on a quantum computer. But the big open question, I think, in quantum computers, is what other problems are quantum computers good for? So we discovered all of these 3 problems, fairly, 3 or 4 years ago, and I think people have been looking for other problems that they're good for, and nobody's really come up with any good ones. In particular, can they solve NP-complete problems? And if they can't, it's going to be very difficult to prove that they cannot, because we can't even prove that classical computers cannot solve NP-complete problems in polynomial time. So we're not going to have a chance proving the same thing with quantum computers unless we're unless someone is very clever. Okay. So I'll get back to quantum computation at the end of the talk, but now I want to talk about information theory. So first, what is information theory? Well, Shannon started the field with one brilliant paper in 1948, and here's a quote from it, which is that the fundamental problem of communication is that of reproducing at one point either exactly or approximately a message selected at another point. And, well, here with quantum information theory, we'll either have quantum, quantum mechanical things you can use to reproduce the information, or the information might be quantum mechanical itself. And Shannon's paper addressed two fundamental problems. One was source coding, which asks how much can a message be compressed for transmission over a noiseless channel. So, if you have computers, you probably are familiar with these zip things, which are gzip, which take a large file, and if it's English or something other than a bunch of random numbers, they compress it to a much shorter file. You can email it to someone, and then they can get the original file back. So that's source coding. And channel coding is if you have a noisy channel, like a telephone line, the question is how much redundancy must be added to a message to ensure faithful transmission over a noisy channel. And Shannon, well, gave answers to both these questions. And, well, for source coding, if you have a discrete memoryless source, S of I, so at each time step it emits the symbol I with probability P sub I, then you can compress it to n times the entropy of the source. So you have n, you take n symbols, you can compress them to n times the h of s plus a little bit, and almost surely get them back at the end. And the entropy is just some pi log of P sub I. And the proof idea is, well, if you look at what this memoryless source outputs, almost all of the time you get something called a typical sequence, which contains approximately n times P sub I symbols of type I, where you have to put error bounds on this approximately, but it's fairly straightforward to do so. And it's easy to see there are only 2 to the h of s times n typical sequences. So you just label the typical sequences in some efficient way, and then you get something from the source. You figure out which of these typical sequences it is, and you just send the label of the typical sequence. And if it's not a typical sequence, this is one of the times where you don't reproduce it exactly. And there's another theorem of Shannon, which says suppose you have a probability distribution on, suppose you have a channel which, you have some number of symbols you can put into the channel, and then there's some other set of symbols which will come out of the channel, and then there's a probability for each symbol in, and what's the probability you'll get that symbol out. Well, the rate at which information can be transmitted is over this channel. If you choose a probability distribution P on the input symbols, that's just the mutual information between the input, which is a random variable, and the output, where mutual information is, well, it's the information, it's the entropy of the output minus the entropy of the output given the input, which is also, can be expressed in several other ways. And the capacity of the channel can be found by maximizing over the probability on the input symbols. And of course, there are generalizations of these theorems for when you don't have, the source is not memoryless, you have the Markov chain and everything, but I won't go into these right now. So, let's see. Where was I? Okay. So now I want to tell you what some of the analogs of these theorems are for quantum mechanical channels. So in quantum mechanics, very often fundamental objects are taken to be pure quantum states, and density matrices are derived from these. And I'll tell you what density matrices are in a little while. But pure quantum states are unit vectors or arrays in C to the n. And a density matrix is a Hermitian trace 1 positive semi-definite matrix over C to the n. And there are two ways of which density matrices arise naturally from pure quantum states. And in quantum, well, at least in what I'm going to be saying next, we're really going to be using density matrices a lot. So I'll tell you a little about them. Well, the first way they arise is, suppose you have a quantum system in state v sub I, which is in state v sub I with probability p sub I, then the density matrix is just summation pi, vi, vi dagger. And one very nice thing about density matrices is, well, there's lots of different ensembles of states and probabilities that give the same density matrix. But the density matrix tells you as much information as you can know about the outcome of any experiment you can do on an ensemble of states with the same density matrix. So two systems with the same density matrix are really indistinguishable without additional information. And yeah, so this is the first way density matrices arise. The second way is if you have a tensor product of two quantum systems, say C to the A and C to the B, and you just are allowed to look at one of these tensor product spaces. If you hold part A, then the density matrix of that part is rho sub A, which is the partial trace with respect to B of rho sub AB. And if you write the matrix this way, where these, this is B11, B12, B1A, and this is C sub A, then when you take the partial trace, you just take the partial trace of each of these submatrices. And partial trace, of course, is coordinate invariant operation. Okay. So now we have density matrices. We want to say something about quantum channels. Yeah, I'll define quantum channels now. Well, quantum channels, well, one thing they need to do is take density matrices to density matrices, because you stick a quantum state in, you want to get a quantum state out. So that means they have to be trace preserving, linear because quantum mechanics is linear, positive, that just means that you put a semi-definite positive matrix in, you get one out, map. So this is clearly necessary. One question is this sufficient? The answer is no. You need to have completely positive maps, which means even if you take this map and you tensor product it with an identity map on another system, it's still positive. And there's a beautiful structure theorem that I believe is a corollary of Davy's theorem for completely positive maps, which says that a completely positive map is the summation of I, A sub I, rho, A sub I, Hermitian transpose for some set of A sub I matrices A sub I with summation I, A sub I, dagger A sub I equal I. And one thing is that not all positive maps are completely positive, and working in quantum information theory, we figured out recently a new way to construct positive maps that are not completely positive, which well, there weren't that many examples of them around before, and I don't know if this new way of constructing them is going to tell us anything interesting or not. But let's get back to quantum information theory. So I think the last ingredient I need to give before I state the theorems is the entropy of density matrix. And it's just the Shannon entropy of the eigenvalues which is minus the trace of rho log rho for the density matrix rho. And von Neumann worked this out by using thermodynamic arguments. And one thing you can ask is this the right definition information theoretically? So, is this the right definition for quantum information theory? So the answer is yes, at least for source coding. So this is a theorem of Schumacher in 1994. And suppose you have a memoryless quantum source that produces quantum states V1, V2, V3, etc., with probabilities P1, P2, P3, and you want to transmit them over a quantum channel. So you want to take this. Well, right now, this is, if each of these lives in dimension K, Hilbert, complex space, quantum space, then if you have n of them, then that's a dimension K to the n space. And you'd like to ask, well, can you compress them into some smaller dimension quantum space before sending them to your friend? So you can use as few quantum bits as possible. Okay, and the theorem of Schumacher is you can send n symbols using n times the entropy of rho plus little o of n qubits with fidelity approaching 1, meaning that the state that their friend gets out is almost exactly the same state you put in as n goes to infinity. Well, how do you do this? So Schumacher did this by, well, classically you do it by looking at typical sequences. Quantum mechanically, you can do it by looking at typical subspaces. A typical subspace is that generated by typical sequences of eigenvectors. So you have a density matrix, and I guess for these, density matrix is 1/2 up, up, plus 1/2 diagonal, diagonal, which turns out to be this with probability lambda 1 and that with probability lambda 2. And so these are the diagonal eigenvalues of it, eigenvectors of it, and eigenvalues. And the typical subspace is generated by typical sequences of eigenvectors. So to compress it, now you can measure whether your sequence lies in S. And if the answer is yes, what you get is the state you started with projected onto S. And, well, the state you started with wasn't exactly in S, but you just have to show that it was very, very close to the typical subspace. And then you can send it using log of dimension S qubits to your friend. And if you get a no, well, this is a low probability event, so you can send anything and the theorem still works. So for Schumacher compression, or for source coding, this is right. Now, you can ask whether that's right information for channel coding, but before I get to that, I'm going to give the theorem of Holevo in 1973. So suppose you have a source that outputs, same source exactly, except it outputs a density matrix rho sub I with probability p sub I. You can ask how much information can you extract from this source?
This is classical situation.
What?
It's classical.
How much classical information?
It's all classical.
No, this is a quantum signal.
It's quantum.
Right. So this is known as called the accessible information, and the definition of this is you have these quantum states, and you have possible measurements, and I'll put up that slide later. But there's a finite set of possible measurements you can do, and then you have if you can a probability rho I. If you start with rho 1, that you'll get outcome M1 or outcome M2 or outcome M3, and then you have probabilities for each of these, and you want to maximize over a set of all possible measurements. But I say finite, it's a compact set of measurements. So there's a maximum, of the mutual information between these and the measurements. And you don't want to just consider von Neumann measurements.
But each measurement changes the speed.
Ah, right. Well, I mean, yeah. So once you've made a measurement, you've destroyed this. Yeah. But, I mean, that's fine. I mean, there's still I mean, you get a sequence of these signals, and you have a sequence of sequence of measurement outcomes, and you want maximize the mutual information between the number of the signal, which is a classical number, and the outcome of the measurement.
So to make one calculation, you have to repeat the experience many times.
Right. Yeah. So what this does is it gives you the most Shannon information you have about which of these inputs you got. And of course you have to, okay, and I am missing a slide. Where are we? Here we are. And what Holevo showed in 1973 was that, well, the accessible information is always less than this quantity, which is a generalization of, I mean, it's the entropy of the input minus this, the entropy of the output given the ith input. Yeah, so yeah, this is the entropy of the output, minus the entropy of the output given the input. So it's essentially the generalization of Shannon's capacity. So Holevo showed that the accessible information was always less than the Shannon capacity, within the, what I'm calling Holevo information. And if all the rows sub I commute, the situation is essentially classical, and they're equal. And if they don't commute, this is a strict inequality. So that looks like, this isn't the right generalization of mutual information. But what we just recently realized is that this was actually the wrong question if you wanted that answer. So, why don't I put the view graph up? So here are two possibilities. This is the accessible information, and here, if you want to use accessible information as a bound for channel capacity, what we're requiring the sender to do is he has to send one of these possible row I for each of these input states. So that means he has to put into the channel, he has to put a pure state into each use of the channel. So what he's doing is he's input over many uses of the channel is a tensor product state. And of course, tensor product states are, and then on the outcome, the receiver just measures each of these separately, gets classical information about the state, puts it into a decoder, and then tries to reconstruct the message. So if you're restricted to this, then the channel capacity is accessible information, which I probably should say is a fairly hard thing to compute, and there aren't that many, there are bounds known for lower upper bounds, but there aren't any exact formulas for it. But if you allow the sender to have a joint product state, not a tensor product state, but an entangled state, and put these into uses of the noisy channel, and then allow the receiver, actually, I take that back. If you still put in tensor product states, but allow the receiver to do a joint measurement on all the outputs, you get the Holevo information out. And that's what this information, this slide says. If you have, if you allow the sender to use signal states rho sub I with probability P sub I, and allow a joint measurement, then he gets Olevo information. So you can ask, is this the right classical capacity for a quantum channel? And the answer is we don't really know. And why not? Well, in that situation, we used tensor product inputs. But you can also ask whether you can do better using entangled inputs. And I think some computations have been done, and nobody has found a case where entangled inputs allow you to send more information, but also nobody has found a proof. And actually, this is equivalent to a very simple, linear algebra question, which is Olevo capacity additive. So you have two completely positive maps, N1 and N2. And the question is CH of N1 tensor N2 equal to CH of N1 plus CH of N2? And C sub H of N is just the maximum over possible input possible inputs to the channel with probability distributions of them of H of the entropy of the output minus the entropy of the output given the input.
And we check for small values, small dimensions.
You can do computer calculations for small dimensions and try to find counterexamples, and nobody has. I think John Smolin has done three-dimensional, I think maybe four-dimensional ones, but I'm not sure, and has not found any counterexamples, but of course this is a huge space to look at. He tried to do some kind of optimization over general N1, N2, and that, but this is a much too large a space to search by computer. So unless you have some clever way of doing it, you're Okay, so that's open problem number 1. And I guess I'm running out of time faster than I thought I would. But one thing I want to show is that recently proved with John Smolin and Charlie Bennett at IBM is if you have, you can do even better than Olevo capacity if both the sender and receiver have access to entangled quantum states, EPR pairs. And in that case, we actually know the answer. And what the answer is a different formula, which is also a generalization of Shannon's formula, which is maximum over, density matrix rho and a density matrix rho tilde, which is, where trace rho tilde equals rho when you trace, so rho tilde is on a larger space, and when you trace out the extra dimensions, you get rho of the entropy of the input plus the entropy of the output minus the entropy of the joint system. So this is also Shannon's formula when you do it classically. So let's see. So now I want to say a little bit more about quantum computers. So in 1994, after I showed that quantum computers could factor integers fast, the typical objection was that errors would make long computations impossible. For example, if you wanted to factor a 150-digit integer, it takes maybe 10 to the 10th steps. And it's easy to show that if you want this calculation to work, each step has to have accuracy 10 to the minus 10th. And this is essentially an impossible engineering task. Well, it turns out that exactly the same objection was raised in the 1950s when classical computers started working. And it turned out not to be an impossible engineering task. So computers we have today just work perfectly. They don't make any mistakes at all, except in software. And, there is, von Neumann didn't foresee this outcome, so he proved this theorem about fault tolerance that says if you have a classical circuit with n gates, you can construct a fault-tolerant version with order of n log n gates, and each gate can make an error with probability epsilon for sufficient, small epsilon, and the circuit will still usually work. So,
It's a strange question, but he proved this theorem, but any of the ideas in the proof actually used in the technology so that proof statement, they don't make any mistakes based on any of that, or is that just a theoretical?
well, so the chips they design today don't have very much fault tolerance built in. In fact, I think some of them don't have any fault tolerance built in, except in memory, and they work fine. They use they do use error correcting codes in memory. So you can ask whether you can do the same thing for quantum computers. And well, you can come up with a list of classical fault tolerance techniques. The one von Neumann used for the proof was massive redundancy, so you just take every bit that's stored in the computer and have many copies of it. There are also error correcting codes where you can protect data stored in memory by just adding a few extra check bits and have very small probability of ever finding an error. There's checkpointing, where you write down the state of the system, and then if something goes wrong after you've written it down, you can recover. And there are consistency checks, where you just make sure that the state of your computer is a reasonable state. It's not an impossible state. So you can ask whether these work quantum mechanically, or for quantum computers. And you immediately run into the problem that you cannot make a copy of an unknown quantum state. And what that does is, let's see. Well, it eliminates most of these techniques, and at first glance it eliminates all of them, but it turns out that number 3, error correcting codes, actually can be made to work. So what is the quantum error correcting code? Well, I'm going to draw the same picture I did before. You start with an unknown quantum state of k qubits, and what you want to do is you want to stick in an encoder and get n qubits out, and then send it through a noisy channel n, and then put it through another decoder. And, well, if you have, say, n qubits here, you'll get n qubits out of the decoder, but n minus k of them will be junk, and you'll have k qubits left in some mixed quantum state. And what you want is that this mixed quantum state is very close to the state you put it in. So it's within 1 minus epsilon, and you want epsilon to go to 0 as n goes to infinity, and this gives you channel capacity of k over n. So, well, there's a couple of questions you can ask about this. And first I'll tell you a little bit about how it works. I don't have time to tell you much about how it works. First, how do you get around the no cloning theorem? Well, what the channel does is it measures a few quantum bits. Or you can think of the action of the channel as measuring a few of your bits. And what you have to do is arrange the encoding state so that measuring a few of the quantum bits gives you absolutely no information about the encoded state, which means all of the encoded information can come out the end without violating the no cloning theorem, because you haven't copied or learned anything about any of it. And essentially what you have to do is arrange the encoding, or essentially how I shouldn't say what you have to do, how a lot of these quantum codes work is you arrange the encoding so you measure the error without measuring the encoded state. And then once you've measured the error, you can fix it, and you still haven't disturbed the encoded state. So let's go back here. You can ask, well, given a noisy channel, how much quantum information can we put through it? And it turns out that there's a lot of noisy channels where you can't get any quantum information through. But here is probably a good guess as to how much the capacity of a noisy quantum channel is. So given a quantum channel T, you can define coherent information. I don't know why this is T and not N. The entropy of the output minus the entropy of the joint system. So this tells you the information of the output, and this really tells you the information about the error. So, well, this is a good guess. One interesting thing is that this quantity is not additive. So for the depolarizing channel, which is a very simple quantum channel where you let the quantum state go through with probability P and replace it with complete noise with probability 1 minus P, the coherent information in 5 uses of the channel is more than 5 times the coherent information in the channel for some, for a very small set of depolarizing probabilities P. So what that means is that coherent information isn't the right answer, but you can ask, well, if you take the limit as n goes to infinity of the coherent information in n uses of the channel, is this the right answer for capacity of a noisy quantum capacity of a noisy quantum channel? And Barnum and all have proved this as an upper bound, but there's an open question: is this the right answer? And there's another open question: when do you need to use more than one use of the channel? So far, for nearly all the channels we know about, it looks like it doesn't help to use more than one, to use n bigger than 1. But for some channels, it does. Okay. So let me say a little bit more and then I'll finish. And hopefully I'll finish on time. So how does fault-tolerant quantum computing work? Well, classically, here's how fault-tolerant computing works classically. You start with, say, AND gate. And what you do to make it fault-tolerant is you make many copies of this bit. And of course, some of them could be have errors in them from the previous step. Make many copies of this bit. Do many ANDs. And then you'll have some errors you've introduced and some errors that crept through from the beginning. And then what you do is a cleanup step where you compare these bits against each other. And then you get a state that's good enough that you can stick it in your next gate. So how do you prove? So one way to do quantum mechanical fault tolerance is the same thing. You have your gate you want to do on these 2 qubits, and you find some kind of quantum circuit which does the gate on both of these and is fault tolerant, and that if you make a few errors in the inputs and have a few errors in your gate, you only get a few errors in your output, and then you do the cleanup steps. And, well, another open question. Well, there's a whole bunch of work on fault-tolerant quantum computing, and what it looks like right now is if each gate is accurate to 1 part in, say, 10 to the 4th, and it may have gone down a little bit since then, you can correct errors in quantum computing. But if each gate is accurate to only 50%, it's fairly easy to see that there's no way to correct the errors. So there's some threshold here. And you can ask, well, what is this threshold? And what kind of phase transition to this really fairly horrible system go through as you go through this threshold? Okay. And so I gave you one way of doing fault-tolerant computation. What I wanted to give you now is there's a really beautiful work of Alexei Kitaev on fault-tolerant quantum computing with anyons. So what he does is he gives some planar graph, say, and then you put quantum states on the edges and vertices, and then you have a Hamiltonian on the system, so there's some kind of ground state. And now you can get this system into states where you have local topological discontinuities so that you can't, so there'll be, here. So your local topological discontinuities, so there's this area of the graph which is not in the ground state, and you can't get into the ground state without changing a whole path between this guy and another anion over here. So it turns out you can do fault-tolerant quantum computing by, well, finding the graph, giving the graph and the quantum variables on it, and then the operations are create a pair of anions, do some kind of braiding of the anions around each other, which topologically changes the state of the system, and then combine two anions to see what happens. And you can show if anions are kept far enough apart, you obtain fault-tolerant quantum computing, because they can't change unless they're brought fairly close together. So now what I want to do is say a little bit about what I think Neyman called metaphysics. So there's this big open problem for the next century, which is how can quantum mechanics and general relativity be unified? And well, what's the problem? Well, one of the problems is that in general relativity, if you throw something into a black hole, it's gone forever, which means information can be destroyed. And quantum mechanics, essentially the very nature of quantum mechanics says that information can never be destroyed. So we have a contradiction. So John Preskill's suggestion, which I really like, is that the universe uses fault tolerance in its operations. So
It means the cells are immortal, right?
well,
No information. Erased.
no, actually, John Preskill says that, so if you look back at this anions, as long as you kept these anions far enough apart, everything looked unitary, but if you bring the anions close together, then you can information destroyed because they combine and create a new anion, and you lose the information about what these two of them look like. So you can ask whether the same thing works for elementary particles. As long as the elementary particles are kept a reasonable distance longer than the Planck length apart, maybe the universe appears unitary. Now, if you bring them close together, maybe, like you might if you threw them into a black hole, maybe information gets destroyed. And there's a really intriguing suggestion, although there's a long way to go from Kitaev's work to theory of quantum gravity, because for one thing, Kitaev's thing is completely static, and you need a dynamical theory, and you need to somehow get it to look like gravity in the standard model. And I'm going to just leave you with this open question.